Thank you, Mr. Chairman. Good afternoon, everyone. My name is Darrin. I'm from the University of Utah. And my graduate student, Sheng, who did the most work here, cannot be here today because of his visa constraint. So I'm here to present to you our research work entitled The Wireless Battery-Free Sub-mW Underground Soil Moisture Sensing System. This is the outline of my talk. I will start off with the introduction of the research project and present to you a ultra-low power tunnel-diode oscillator-based capacitive soil moisture sensor, followed by describing to you a wireless and a battery-free soil moisture sensing system. I will then present to you some of our obtained laboratory characterization results and end my talk with a conclusion in the future work. So world's population is expected to reach 9 billion by 2050, and the increased food production is likely cause severe soil degradation. So we face a major challenge, which is how to maintain soil health and improve efficient water usage for sustainable agriculture in the future. And to achieve this goal, we need to have long-term and in situ soil monitoring technology. So this slide shows a number of commercially available soil monitoring technology or products. And as you can see, these products require pretty intensive labor work in terms of maintenance and data collection. And the products are often battery powered or powered by solar panel, which is inconvenient for standard or for conventional agriculture practice because you have things sticking out of the ground. And they can be expensive and have limited scalability. So the desirable feature that we're trying to achieve are the following. We need to have low maintenance. We need to have wireless capability. We need to have battery-free capability to be low cost, all underground, and readily scalable. So this slide shows our envisioned wireless battery-free underground in situ soil sensing architecture. For example, we can have a ground vehicle traveling over the soil surface with a buried soil moisture sensor underneath to provide wireless and a battery-free monitoring. And in terms of achieving wireless and a battery-free monitoring, we need to have wireless power transfer and a sensor data telemetry through soil. The desirable sensing depth is under order 30 centimeter and beyond, because this is the typical cultivation layer in which the crop will grow. The parameter of interest include moisture, salinity, which ties to electrical conductivity of the soil, temperature, pH, and etc. So for this talk, given the limited time, so we focus on soil moisture sensing capability. So now I'd like to talk about a tunnel-diode oscillator-based capacitive soil moisture sensor design. So this schematic shows the overall architecture of designing such an oscillator. Basically, it consists of a LC tank circuit interfaced with a tunnel-diode oscillator exhibiting a negative resistance around 900 ohm biased at the 0.2 volt. This is just a particular type of tunnel diode we use. Depending on the tunnel diode you use, you may have different resistance value. So if everything is designed properly, which I'll talk about more, we can achieve an oscillator. And a pair of sensing probes made out of metallic rods insert or buried in the soil can form a capacitive sensor we call the C-sense. So as the soil moisture change, the soil dielectric constant will change. As a result, it will change the capacitance value. Therefore, we can frequency modulate the oscillator of frequency. Now, this oscillator transmitter coil serves two purposes. One is acts as a tank circuit inductor. The second purpose is acts as a wireless signal transmission antenna. And this impedance C-trans right here is used to provide capacitive impedance transformation for reliable oscillation. The next slide, you will see some measurement data, then you see why we need that impedance transformation circuit to achieve a reliable oscillation. The oscillator nominal frequency is designed around 40 MHz within the ISM band, and that can be adjusted by the C2 value. And the oscillator dissipates very low power, only 40 microwatt, because at a DC bias of 0.2 volt and a 2 microampere current, it only dissipates 40 microwatt, which can enable us to develop about minus 20 dBm RF power from the oscillator. This slide talks a bit more about the design consideration, when we come to design the oscillator. For example, the picture on the upper right corner shows there are two metal rods, stainless steel metal rods. Each one has a length about 6.5 centimeters, separated by a spacing about centimeter buried in the soil. On the right-hand side is an electrical equivalent model for the sensor. And in this case, we don't have an ideal capacitive sensor. There is certain capacitive loss as a parallel resistor cross over the sensor. So the two plots on the upper right corner shows that when we change the soil moisture level from 20% to about 44%, the capacitance value will increase from 16 puff to 39 puff because the dielectric constant of the soil changed. But what's more important is that if you look at the resistance drops from 760 ohm down to about 100 ohm. That is measured at the 40 matrix because this is the frequency that we intend to make the oscillator work within the ISM band. And if you remember the negative resistance from the tunnel-diode being minus 900 ohm at the proper bias point, this type of resistance is too low to be compensated by the negative resistance. Therefore, we need to add a impedance transformation capacitance of about 5 puff. So as a result, now you're looking into this two-pole model, right? You will have a reduced capacitance change from 3.9 puff to 4.7 puff over the moisture range from 20% to 44%. But what we gain is now the overall resistance looking into it is over 5,000 ohm over the moisture range measured at that frequency 40 megahertz. So the oscillator transmitter coil is implemented using this wire with a dimension about 6 centimeter by 1.5 centimeter with 3 turns. We can achieve an inductance value of 540 nanohenry with a Q factor of 24 at the 40 megahertz. So when you combine this impedance, the inductor impedance with the capacitor network, we can achieve a tank resonant frequency about 2 kilo ohm at the 40 megahertz. Now, when you compare to 2 kilo ohm and a minus 900 ohm, if you work out the math, right, you can see that can be effectively compensated by the tunnel-diode oscillator for reliable oscillation. So the oscillator frequency can shift around 720 kilohertz for soil moisture ranging from 20% to 44%. So this slide gives you kind of a high-level design for the wireless and the battery-free soil moisture sensing system. So that it has two parts. On the top part, that's the wireless power transfer part. We call it inductive power transfer from inductive coil L1 to L2. The L1 is the coil above the ground surface, right? That transmit the power down. L2 represents a coil that's buried underneath the soil with a distance for this design is about 30 centimeters. So the coupling, inductive coupling, is achieved through the mutual inductance. Now, the first coil, L1, is designed with a diameter of 40 centimeters and 2 turns that achieves a 5 microhenry inductance with a maximum quality factor Q around 300 at a 2 megahertz. The L2, which is the secondary coil buried under the soil, is designed with 6 centimeter diameter and 4 turns, providing us with an inductance of 1.33 microhenry with a maximum Q value of 210, around 2 megahertz. So therefore, we design our power transfer operating frequency at the 2 megahertz to maximize the performance because we can achieve the maximum Q at that 2 megahertz. And you may wonder, is this a coincidence? Of course not. We design our coil with size and the turns to hit that number, right? If you have something different Qs, different Q max, a different frequency, it becomes a harder tuning issue. And the 2 megahertz is also desirable for us to minimize interference with the sensor FM signal that is occurring at the 40 megahertz. So the L2 size, right? The L2 size, 6 centimeter diameter and 4 turns is chosen for a compact underground system design. And the L1 side is chosen to maximize the mutual coupling inductance with 30 centimeter gap from the L2, and also the relatively large size, 40 centimeter for the above ground coil, to reduce the misalignment sensitivity in field operation. And in the design, we incorporate a rectifier followed by a voltage regulator that is used to convert the received RF power to a 0.2 volt DC that is used to energize the oscillator. Therefore, that provides the powering scheme, right, for a battery-free sensing system. The overall system in this case dissipates 0.32 milliwatt compared to the 40 microwatt power in the oscillator. You can see that the power is really dominated by the voltage regulator, and we achieve inductive power transfer efficiency around 3% for the size of the coil we choose and the 30 centimeter distance we're trying to cover. Yeah, so now let's just quickly talk about some of the laboratory characterization results. So the top three pictures shows what we do in our lab. For example, you can see this is a 3D printer package, and our electronic components consisting of RF power receiving coil, that is the 6 nanometer diameter coil we call L2, and the oscillator transmitter coil, that is a 6 centimeter by 1.5 centimeter size. They are aligned, they are positioned in the orthogonal manner inside the package to minimize the RF interference. And we have capacitive soil moisture sensing probe sticking out of the package on the side. This line in the middle shows that the package, the overall system, is positioned inside a bucket with soil underneath. And on top, we have about 40 centimeter gap, which will be filled by soils. And once the soil fills the entire sensor, we have that external RF power transmitter coil placed on top, which will be used to send power, 2 megahertz power, cross over 30 centimeter distance to energize the sensor. Once the sensor gets energized, it will transmit a FM signal around 40 megahertz that's indicating the soil moisture level. And we use the antenna attached to the spectrum analyzer serving as a receiver in our lab to receive the signal. So this is just down here, it's a wireless receive power spectrum from the Barry sensor. And on the right-hand side, this is the measured time domain waveform. It shows that this is our input RF waveform, and this is the received RF waveform. And this purple line is a 1 volt DC signal out of the voltage regulator, which will be used to energize a voltage, this out of the rectifier. And it will be used to energize the voltage regulator that outputs 0.2 volt DC to energize the oscillator. So this slide shows some sort of interesting measurement plots. Upper down right corner shows that we have the received oscillator frequency versus moisture level. And the oscillator frequency can shift from 38.6 megahertz down to 38.02 megahertz, corresponds to a range of 580 kilohertz, for the moisture range from 19% to 45%, indicating that we have a sensitivity about 25 kilohertz per percent moisture level change. And we also look at the oscillator frequency drift in air. It shows that it has a temperature coefficient about minus 13 kilohertz per degree C measured over 30 hours. So in the future, we will incorporate a temperature sensor, right, to provide temperature compensation for the frequency. And this slide shows some of our ongoing sensor field test. I did that a few days before I moved here last Thursday. That was not included in the preceding paper. This is like very recent data. It shows that we have our package sensor that's buried 30 centimeter below the ground, and the primary RF coil that is mounted on a wood frame attached to a metal 3-point tractor implement. The purpose of doing that is to minimize the Q degradation due to metal surrounding. And this is the field test, picture. We have sensor buried here, and this is the coil on top. This is the received power spectrum. So far we have demonstrated wireless and the battery-free operation in field. So now I'm going to conclude my talk with some conclusion of future. We have demonstrated a wireless and a battery-free soil moisture sensing system. The prototype system is operable at the 30 centimeter below the ground surface. and it can potentially enable a low-cost, low-maintenance field operation with large scalability, and it can also enable improved efficient water usage for future sustainable agriculture. Our future will consist of continuing the ongoing sensor field test, investigate sensor performance in various types of soil in terms of sensor validation and calibration. And we are also in the process of building a multi-channel wireless battery-free soil monitoring system. That system will include not only the moisture, but also electrical conductivity and the temperature. And we'd like to acknowledge the U.S. National Science Foundation for this research project. Thank you.